and I'm looking forward to this because I think this is one of the areas in graphs that that is evolving very quickly right now, and I don't think we know exactly where it will land yet, but it's super promising.
For sure. Yeah. Yeah, I think this is definitely one of those areas in the AI world. I think it's interesting to watch how things kind of evolve because there'll be like a bit of push ahead in say like the quality of the models, and then people will talk about, oh well the models are, you know, plateauing, but then we'll see like a big boost in maybe like the application layer or the framework layer. MCP, like the adoption of model context protocol, I think was a great example of this, where we see we see things in the AI ecosystem kind of pushing the envelope and moving sort of how we build AI applications forward. And so I think memory and graph memory especially is one of those right now that we're seeing things moving forward in that area, especially. So yeah, so let's dive into it. If you don't know me, my name's Will. I work for a company called Hypermode. We make an AI agent platform, and we also maintain the open source graph database. Curious if anyone is using dgraph. Let us know in the chat. Just curious. We're not going to talk much about dgraph today. I'm going to show some examples using Neo4j. If folks are using Neo4j, let us know too. Just curious about that as well. You can get the slides, this QR code or this link. Let's see if I can drop this in the chat. It's just graphstuff.com.
And Will, there's also a chat within the Riverside tool that we happen to be using, uh, if if that's easier to follow on the far right.
Oh, cool. Cool. I see that
Yeah.
too. Awesome. Cool. So that's the slides. A little bit about me. Let's go ahead and jump in. So I want to start off just by kind of taking a look at a high level of like what is the like common architecture, what are the typical components for like an AI app. And we're talking specifically today about like AI agents and memory, but we'll see how that those concepts kind of fit in and use that as a bit of motivation to talk about like why do we even need memory, and then why is using graphs for memory like really a big benefit and a big boost, and like why is this so interesting right now. We're going to take a look at this through an example project that I built that I called Go Fetch, just kind of to demonstrate some of the concepts today, and then we'll leave plenty of time for questions and take a look at some other resources to dive in. So just to get started here, let's take a high level look at like what are the components of an AI agent. And I think Anthropic in this blog post, Building Effective Agents, I think really did a good job of, you know, pointing out that at a fundamental level, like agents are all about being able to interact and understand their environment. And we're able to do that by augmenting the model through like retrieval, where we're maybe fetching data from a database based on the specific query or user message from the user, right? Something like RAG, retrieval augmented generation, where we're injecting into the context data from a database. Tools, these are the ability for the models to call functions or interact with other APIs or services, and then this concept of memory. And there are lots of different kinds of memory, but you can think of memory as distinct from retrieval, I think, because it's something that is constantly being updated. When we're thinking of RAG and retrieval, those are typically like static documents that we're working with, or maybe they're updated in batch. But memory, this is something that is constantly being updated in real time as we're interacting with the agent, or maybe like a team of agents. Maybe this memory is shared across users, that sort of thing. So taking that idea of the augmented LLM and that concept and looking at, okay, what's the typical architecture of an AI app, of an agent app? Well, typically, we have some orchestration layer. That's this big box in the middle, and typically this is handled by your agent framework. Uh, at Hypermode, we build and maintain an agent framework called Modus that they handle some of these things. Other frameworks that do these sorts of things are like Google's ADK or LangChain, Llama Index, those sorts of things. But fundamentally, the orchestration layer is dealing with this concept of orchestrating user messages, the system prompt for what we are sort of defining as like the goal and task of our agent, uh, sort of orchestrating the interaction of that like natural language coming in from the user and the system prompt with calls to the LLM. The LLM is given tools. These can be the ability to fetch data from external services, MCP and the adoption of Model Context Protocol, and sort of this proliferation of third-party services building MCP servers makes it much easier for your agent to, say, integrate with Google Docs, GitHub, Slack, using the tools exposed by those MCP servers. And we'll talk a bit more about MCP in a moment. Then on the other side here, we have this concept of data and knowledge that this orchestration layer is responsible for. It's responsible for making sure that we have the correct data in the context at all times. I think this concept now has the term context engineering, which is sort of, I don't know, maybe like an evolution of prompt engineering, where it's kind of pointing out that like we're it's really, really important for the model to have not just like this huge bloated context. We can't just inject everything to the context. Instead, we want to make sure that we have the correct and most relevant context for our agent at any given time, and we can do this through retrieval or also through memory. That like I talked about like this key difference on the previous slide, the difference of like retrieval and memory, and I said that like retrieval that's typically like going after some static group of documents, maybe in a vector database or something like that. Whereas memory is much more like streaming, updated in real time. Our agent is also writing to that memory layer as well. And so I typically think of retrieval as like something external to the uh, the agent framework that we're using. Of course, we need to have abstractions for how to bring that data in. Whereas memory is typically something that is a lot closer to our agent framework. Maybe it's managed by the the agent framework, or maybe there are like different abstractions for different plug and play memory. But some distinction there of how we think about memory and retrieval. Let's talk about, why do we even need agent memory in the first place? Here's a simple example that I think some folks may have experienced with, various agents. It's like in your first session, you say, hey, I'm working on a Python project for data analysis. I want to use pandas instead of NumPy, whenever possible, and generate some code for me. And so, like, okay, cool. Like you told me that you like pandas. We're gonna do pandas instead of NumPy. But then you start a new session, and the agent's like, well, I don't know. Like, what libraries do you want to use? Maybe I'll just pick one. Whereas if we have agent memory, where the agent is actually able to store that information, store these user preferences, like, oh, this user prefers pandas. They're doing data analysis. So then we have this like continuity as we interact with our agent that is able to save and understand and have our preferences in the context in that call to the LLM. And so that's just one kind of like simple example. I think being able to add your sort of own business data, right? So generic responses or even hallucination, right? This is kind of the common problem that you have without agent memory. Trust is a big issue, I think, right now in the agent space. I mean, if you think about on this previous slide, like we're giving our agent access to all of these services that we're authing in through MCP. We're spending a lot of money on our LLM invocations. We want to like have trust in these like very simple interactions that we have with agents, like generate some Python code using libraries I prefer. Like we kind of need to pass that like trust gate before we can move on to more more like production and more important like enterprise-wide use cases. Efficiency, right? Like avoiding repetitive information gathering. It's annoying when you're like telling the agent your preferences over and over again, but apply that to, I don't know, maybe something where there's an expensive like deep research phase, or you know you're applying this throughout your enterprise. That inefficiency can really add up to significant cost. And then the final one here, this is actually, I think, really interesting, and this is something we're digging into at Hypermode, is this concept of like learning a task, right? So you go through some workflow or some successful interaction with your agent. You want to be able to like save that learning of here's how we go through these steps. You want to be able to sort of save that knowledge for your agent. There are different
So
kinds.
the
Yeah, go
other
ahead.
um, the other thing I was just going to add, Will, is that for context windows, I've also heard that you can overrun the context window if you have multiple really large documents that you're trying to compare and contrast. So there's also, if you're doing, as you said, deep research, but also trying to pull in documents from multiple locations and then do like multiple novel size worth, reviews, that can be very limited if you don't have a bigger memory window. So.
Totally, yeah, and I think the pushback to building some of these more complex memory systems are like, hey, context windows are constantly growing. Um, I can jam like a million tokens into the context of some of these new models. So I can just shove all my documents in there. I don't need to worry about properly managing context, and I don't even need to think about this memory thing. And to your point, like you can really blow up the context window with inserting multiple documents and these sorts of things, but especially with tool calling. And I think there's now with the proliferation of MCP, there's like more and more tool calling agents. Think about all the data that comes back from that. Like in anything that comes back from a tool call is living in the context. So if you're querying a database and you return 10,000 rows from that, that's going to live in the context. So something to consider for sure. Cool. So our example was kind of like user preferences that we saw, right? When we were talking about that Python example. So that's kind of like a personal memory, right? Where we're talking about user preferences, style, individual characteristics. But we also have other types of memory. So this could be like working memory, where we need to maintain context, within a current conversation or across conversations. Episodic memory, where we're storing like experiences and events from past interactions for the agent to take into account. And then procedural memory, where we're sort of learning how to perform a task in a workflow. There's some similarities, and it can be kind of hard to figure out where exactly your use case falls. But we'll touch on these different points today. So I should say that a lot of what I'm going to talk about today comes from three specific papers. The MIM-GPT paper I think is really interesting because it talks about introducing, I guess, this concept, and it's really talking about like how can we expose memory tools to the agent so that as you're interacting with the uh, as you're interacting with the agent and your agent sees like, oh, here's a new fact, here's a new like user preference, that sort of thing, and it's really up to that model that is powering your agent to then call these tools to update the memory layers. This one I think is like a good um, conceptual idea of like, hey, and borrow some ideas from operating systems. So if you were a CS student and you had to write like an operating system from scratch, there are some fond I don't know, recollections there, I guess. And then the other two papers are like practical implementations of some of the concepts there. And one is the ZEP paper, Temporal Knowledge Graph Architecture for Agent Memory. This comes from the ZEP AI team, which is doing really interesting things around agent memory with graphs. They build and maintain an open source agent framework called Graffiti. Graffiti is open source and uses Neo4j to construct knowledge graphs from agent interactions, and then allows you to search that graph to update context based on the knowledge graph that you've built from interactions with the agent. And then MIM0, which is I guess this paper is interesting in two cases. One, because it kind of points out like the MIM0 system, and then MIM0 graph as kind of an extension to that. So you can kind of see how these concepts can be applied without the graph, and then the benefits you get by applying the graph. And I should say one thing that Graffiti and ZEP like really focus on is this idea of the temporal knowledge graph. And they do a lot in this paper to talk about why the temporal aspect is really important, right? So, like your preferences can change over time, these sorts of things. And by having relationships in the graph, we can be able to take that temporal aspect into account, right? Like certain relationships between entities may be overridden or no longer valid. In RAG or just like a vector similarity search, that concept is really difficult or impossible to get across. But in the graph, those sort of temporal relationships are really important. So I'd say that's a big part of the Graffiti paper as well.
And I really like these papers because they have different approaches. And like one will show more accuracy but more token usage, and the other, more efficient. But again, accuracy is a little different. I would say I think it's Mem0 that kind of points to more of a memory hierarchy as well, which kind of likens back
Mm.
to operating system hierarchy and things like that. So I think they're really good foundational papers to read, and I'm sure there's going to be a lot of other ones as well that come out. Yeah.
Totally, for sure. In fact, I have where are they now? Yeah, I have my little notebook here of printed papers left to read. So
There you
I have a
go.
few more there.
Yeah.
Maybe at the end we can, if we have time, we can take a look at what papers I have in there, and folks can suggest other ones that
Oh, that would be
might be a good
awesome.
read.
Yeah. Yeah.
Maybe we should do like a Graph Geeks paper reading club or something like that. Or maybe I
I
already do
I'm
that. I don't know.
I'm
Do you?
we've talked about it, and I think right now I'm searching for somebody to help lead and organize that. But there are several people who are really excited about doing like a instead of a book club, do a reading club. So plug for that if people are interested in actually leading and just help organizing folks. So
Cool, cool. I like that.
yeah.
So yeah. So anyway, so that's kind of where the the context for what I'm going to talk about comes from. There are lots of different approaches, but what we're going to look at largely comes from these papers. So let's dive into kind of the methodology here. Oh, and I should say the this methodology comes from a project that I wrote, which we'll take a look at in deeper detail, which I think I have open in another screen here. I don't. Let me drop a link to this just so you can see what we're going to look at. So this is the project we're going to be using to dive into um, our example in a minute. If why that loads, there we go. So I called this Go Fetch, which is very much a backronym, graph-oriented fast edge traversal cache hub, which doesn't really mean anything. But the reason I named it this, I'll go on a small detour here. I was reading some of these like RAG papers, and in these RAG benchmarks, there's this concept of the the golden document, and so they're like testing to see if your RAG system is able to retrieve the correct document, and that's like the golden document, and that got me thinking of, well, you have kind of like a golden retriever then, if that's what you're doing when you're comparing RAG, is you're like comparing which retriever always finds you that golden document, which got me thinking of golden retriever that likes to play fetch. And so anyway, so that's how we came up with the name there. But really, with this project, I really just wanted to demonstrate like some of these concepts of how do we construct a graph from agent conversations, and then how do we allow our agent to search that graph. That's essentially like the two big concepts here. And initially I wrote this for dgraph, but then I added in Neo4j support as well. So you can have like pretty much the same functionality using either dgraph or Neo4j. You just kind of have to choose which credentials you stick in the configuration is basically how you choose one or the other. And then for the models, this will work with either Anthropic, OpenAI, or locally with Olama. And so there's hopefully like a pretty extensive README here if folks want to see how this works. But we'll get to this in a moment. But anyway, that's what we're going to be looking at. So as we're going through this and full screen, there we go. As I'm going through this and sort of talking about the methodology, that's kind of the specific lens that we have for this project. Cool. I think Amy dropped, so I will do a better job of monitoring the chat. But yeah, feel free to keep up the chat. Thanks for that. Cool. So yeah, so the first step here is graph construction from unstructured data. This can be like user messages. So this could be chat between a user and an agent, or this can also be something like documents that we're inserting, or perhaps like JSON documents, things like that, business data that we want to include as well. And then we're going to talk about how do we actually expose these tools to our model once we've built them. So first of all, graph construction from unstructured data. So the first step in this is going to be entity extraction. And so we use a prompt, we use the model to extract the entities. This prompt is adapted from the ZEP paper. I'm not sure, it's probably, I don't think it's exactly the prompt, but very similar to what Graffiti is using in the ZEP paper. So we're essentially saying like, hey, like based on the current message, like what are the entities that we are mentioning? And so if I use an example text, which I didn't put here, but basically the example text that I want to use is like William Lyon works at Hypermode. He's currently in Yellowstone National Park. He's traveling to Colorado Springs, where he is presenting next week at the Dev to Next conference about AI native app architecture. So that's the text that we're using for this example. And so we find all of the entities, and the entities can be like people, locations, a concept in this case, like this is the topic I'm going to be talking about. They can be businesses, that sort of thing. But then the next step is entity resolution. This step is really important because we don't want to create duplicates in the graph. We want to make sure that we have like we're talking about the William Lyon, we want to have like a William Lyon node, like a canonical representation of the thing is really important. So in entity resolution, there are a few different ways to go about that. I think it's a little bit beyond the scope of what we're talking about. There's some great content on the Graph Geeks network. I know Paco's done a lot of work on this, talking about entity resolution in knowledge graphs. The example that I use in the Go Fetch project is super simple. We just have a name for each thing, and we just look at the name. And so there are lots of other more sophisticated things that we could be doing there, like looking at fuzzy text matching, looking at like the context of how the entities are mentioned, that sort of thing. But use a fairly simple approach there. Then the next step is relationship extraction, or like what are the actual facts in our message. This is the prompt, because again we're going to use the model for this, and again this is adapted from the ZEP paper. And so essentially we're just asking, like, identify relationships between the entities that were mentioned, and then we will also want to come up with like a way to describe that relationship. And in Neo4j in the property graph model, we typically use these like works with, located in, member of, these sorts of relationship types. And so here our graph is enhanced a little bit. So William Lyon, currently in Yellowstone National Park, works for Hypermode, traveling to Colorado Springs, speaking at this conference, and then a topic, AI native app architecture, at the conference. Similar to the entity resolution step, we need to do a relationship resolution step. Like, do we already have this, William Lyon works for Hypermode relationship in the graph? Is there new information here? Do we need to update it? That sort of thing. The next step is the temporal relationship piece, which again, we use the model to do this. And this one, again, this prompt was adapted from the ZEP paper. And here we're really, looking at saying, okay, is this the date that the relationship became valid? Is there an invalidation of the relationship? This is where the relationship resolution piece is important, because it may be a fact that like I have some preference, that preference changes, and I'm not going to, I don't know, maybe delete the relationship or create a new relationship. I'm just going to change the date. So that piece is really important. Here's a couple of examples. So William Lyon works for Hypermode, valid as of today, since that's when I set it. And then William Lyon speaking at Dev2Next conference, well, that's going to be October 1st. And so we're going to save that temporal information on the relationship as a property. One thing that really surprised me is that models are actually quite good at geocoding locations. Geocoding is this idea of, if I have some description of a place, so like here I have Yellowstone National Park, Colorado Springs, I want to convert that into a latitude and longitude, and into a point, so that I could then use a spatial index, for example, to say, oh, okay, find all of the things that are like within 100 miles of Colorado Springs, or things that are within Yellowstone National Park. Models are actually pretty good at that. There are, of course, like geocoding APIs that we can call out to, and this sort of thing. But I added this step in here because I think the location information is an important indexing layer as well. So we do that. We geocode any location entities just to add the latitude and longitude. And then we're going to generate embeddings. So vector search is still going to be like an important like entry point into the graph. So we're going to generate embeddings for things like the memory itself and then the names of any of the entities. I'm not going to show this in too much detail, but this is one thing that I think is quite fascinating is how we can apply graph algorithms like community detection and centrality to our memory search. And so we'll also run community detection algorithm on the entities so that we can see how those entities sort of break down into communities. And when it's time to retrieve entities and memories, we may be able to leverage those communities by traversing the community. Cool. So that's the basic concept for constructing the graph. Let me pause here and see if there are any questions. Feel free to drop any questions that we have in the chat. Let me just scroll through here quick. Cool. So I see some questions about the papers. Thank you, Amy, for posting links to those. Question about performing any kind of encoding of the node level. Yeah, so that's the embedding piece, which we'll see. So we generate embeddings and store those in vector index for the, yeah, exactly, node level metadata. Yep, exactly. And we'll see how we use that in a moment. Cool. I think, yep, and we'll share, yep, so I shared a link to the code. I see some questions about that. Okay, cool. Otherwise, I think I'm caught up. If I missed anything, drop it in the chat again. Cool. Oh, cool. I see a question from Raf here about temporal information added on the relationships. Makes me think about innery relation where we want to link several information in the relations. Have you seen that in the papers? So is that kind of like a hypergraph, Raf, then, where we have kind of like multiple relationships or multiple nodes connecting a relationship based on the temporal piece? Is that kind of what you're getting at, Raf? I think the way that I've seen it used, and I think this specifically comes in the ZEP paper, uh, digging into the temporal aspect and like the benefit that you can get by enhancing the graph with temporal data is really all about invalidation. And so if I have a preference and that preference changes, that's really difficult to express in just like a vector database, right? Or like in a similarity search because I have the preference. I have a difficult way of expressing the relationships between, say, like the user and the preference. But we can invalidate that in the graph simply because like it's by updating that relationship property. Yeah, exactly. Cool. Well, let's talk about the other piece of functionality, which is graph search for memory retrieval and managing our context. So far we looked at the methodology for constructing the graph, and that is sort of how we're going to add that into the graph database. But now, how do we actually like expose the memory to the agent to be able to update? And essentially here, there's a few different steps. The like vector search, I think, is important as just like the entry point, but then we're traversing that. So what we're going to do, for example, is if we are searching for something about specific location or specific concepts based on my my chat with the agent. We're going to use the vector search as the entry point to that. So we'll do a similarity search, but then traverse the graph to find all of the related entities. We'll use the community detection to find the communities and grab all entities within that community and the memories connected to those as well. So that's essentially what we're doing to expose graph memory search to our agent. I should say that that's how we build the functionality for that, so we can construct these tools. But now the question is, how do we expose those memory tools to the agent? And one way to do that is via MCP, or Model Context Protocol. I'll talk maybe just a little bit about Model Context Protocol. I think there's, it's a pretty popular way of exposing tools to models at this point. So if you're not familiar with MCP and you're working with AI agents, it certainly will most likely be something that will come up. So an important concept to understand. Fundamentally, MCP, or Model Context Protocol, is a protocol that defines how we can expose tools to models to allow them to interact and understand their environment. And so essentially, like in this diagram here, we have our AI applications. This can be like our chat interface, like Claude Desktop. This could be an IDE, right? Maybe we're in something like Windsurf or Cursor, or really any AI application. And then on the right, we have these services, like we have databases, we have productivity tools like Google, Slack, these sorts of things. We want to be able to expose tools to search and update these data sources and services to our AI applications. Model Context Protocol enables that. And it does that by exposing tools, resources, and prompt templates to the AI application. So there's an MCP server, which we're going to take a look at in a moment, that exposes the tools. And also what's interesting about the way that tools are exposed with MCP is the natural language description of them. And so our model needs to understand what tools will do, what their inputs are, what like parameters the model needs to generate to call them, what the response are, that sort of thing. MCP servers can also expose resources. So resources, is like read-only data. We can give access to files or database records, and then also prompt templates, which are like predefined prompts for your AI application. Not all MCP clients support resources or prompts. So tools is I think right now kind of the main focus of MCP. I borrowed this slide, by the way, from a deep learning.ai course that talks about how to build MCP servers and clients. So it's a great like short course to go through if you're interested in learning more about MCP, not just like how to use and consume MCP, but also how to build MCP servers, which is quite interesting. Okay, cool. So that's kind of a high-level overview of MCP. Let's take a look at how we can see this in action. But before that, let's take a look at the chat here. Yeah, can I say how I'll be leveraging the graph relationship in our app? Yeah, totally. We'll take a look at that in a moment. Essentially, what we're going to be doing with the graph relationships is seeing how the entities that we are mentioning in our agent interaction are connected, and then we're going to be leveraging those connections in graph search for our memory that's going to be injected into the context. But yeah, we'll see a more concrete example of that in a moment. Another question here from Global Graphs, model entities and relationships within one agent. How does this scale across multiple agents or organizations? A schema negotiation layer, or will every graph remain siloed? Yeah, so that's a good question. So we're kind of talking about this in the context of like a single user and a single agent and interactions between one user and one agent. But of course, like we have agents being adopted in enterprises, with teams of users. We often work with multiple agents and this sort of thing. One thing that's nice about using a graph database like Neo4j or dgraph is that we can simply share that database memory layer with other agents. Now, of course, we need to think about how to express this in to your point, Global, you bring this up, like how to express that in the graph schema that we're going to like maybe like a multi-tenant knowledge graph, that sort of thing. And there's definitely cases where we want only like a single knowledge graph for a single user and single agent. In fact, in Modus, the open source framework, we use an embedded graph database in each Modus app. So there is a like embedded graph database there just for like those agent user interactions. But then you can also take like enterprise-wide knowledge graph, like dgraph or Neo4j, and expose that across multiple agents. I think that is, I guess, one evolving area in this like graph memory aspect that I think is interesting to think about. I have a little bit more of that on the end, but yeah, that's a great question. Thank you. Cool. Well, let's take a look at this in action. So I mentioned this earlier that I wrote this, I don't know what we want to call it, a graph agent memory sort of sampled framework. It's really an MCP server. It exposes memory tools via MCP, one for constructing the graph and one for searching the graph. We can use either Neo4j or dgraph with this, and again, either OpenAI, Anthropic, or Ollama. The GitHub repo is linked here. And there's two tools that are exposed, right? The memory search tool and this save message tool. And I kind of walked through like the methodology for each of these, so I won't go into a huge amount of detail. But the basic idea is we can pass in either a user agent conversation, a document, maybe JSON data, and go through these steps of entity extraction, entity resolution, building the temporal components, updating the graph algorithms, that sort of thing. And then the memory search tool will leverage the embeddings that we've saved in our entities and memories that we've saved in the graph, do this sort of vector similarity search as the entry point for our graph traversal. We'll also leverage the geospatial information as another index layer there. And then the point of this that we get out as the response from our memory search tool is like what we need to update our AI agent context with. This is the graph data model that we create. This applies for both dgraph or Neo4j. So dgraph is a property graph database. You can see here essentially we're identifying the entities. We're adding relationships, so like how those entities are connected. We could store these as the relationship type, or in this case, I just added a type property to the relationship. That makes the traversals easier, specifically in dgraph, but just kind of, I think does a better job of like keeping our graph data model a bit more constrained by using a single relationship type. But certainly we can iterate on this. And then the community aspect too, we create a community node, and then entities that are within each community are connected to that community node. We can also then generate like a summary of the community, which I think is really interesting, based on the description of all of the entities connected to it. Cool. So let's see this in action here. So let's jump to our editor and let's just go ahead and give this a run. npm run dev. So I should say this is a TypeScript application. It uses the Vercel AI SDK. And also is using the TypeScript MCP library. So it's actually quite straightforward to create MCP servers this way. I don't want to go through the code too much, and you can kind of scroll through that on your own. But let's just see how this works, and then we'll take a look at some of the code here. So I started the MCP server, and so one way that we can debug our MCP servers is with the MCP inspector. Curious if anyone's um, built an MCP server, let us know in the chat. 'Cause I'm curious how folks are sort of progressing with building MCP servers and like what language folks are using. Python is popular. I chose to do this one in TypeScript really because I wanted to leverage the Vercel AI SDK, which is another area I could dive into and talk about for a long time. But the MCP inspector, this is tooling that allows us to connect to an MCP server and we can like see the tools that are available. So there's two tools. There's save user message and a graph memory search. We can invoke our tools from here. So let's go ahead and do that. So I had this sort of sample paragraph that I was using earlier here, which says William Lyon works for Hypermode. Traveling currently in Yellowstone Park, traveling to Colorado Springs for a conference next week where he's speaking about AI native app architecture on October 1st. And so this is running. If we take a look in the debug output here, let's see. We started up here, and so the first thing that we do when we start the MCP server is update the database constraints in Neo4j. That's what the schema query is. And then here we got a MCP request, and we can see here, like here's the text. We send that to the LLM to identify the entities. So it found 5 entities. William Lyon, which is a person, Hypermode, which is an organization, Yellowstone National Park, which is a location, Colorado Springs, which is a location, Dev2Next conference, which is an event. And then we go through the entity resolution step, which is basically just do we have other entities that have this name? And then we generate embeddings for each of those and save those as properties. And then we are adding the relationship. So William Lyon traveling to Colorado, William Lyon speaking at Dev2Next, that sort of thing. And we're doing the geocoding process as part of the entity resolution as well. And so if we jump to our Neo4j instance, which I think we have here. Yep, cool. You can see here that, cool, yep, I have 5 entities. I can see how they are all connected. And so we end up with one memory node. So we store like the full content of the memory in this memory node. We store the embedding for that. And then for these entities, here's Yellowstone National Park. It has a location. So this is the latitude and longitude that we use the model to geocode. We generated an embedding. We have a description for it. And we can see its relationships, right? So William Lyon is related to Yellowstone. If we look at the relationship type, currently in is how we are relating that. We're saying that William Lyon works for Hypermode, and you can also see the temporal component, like here's the date that this is valid. If we look at the like the dev to next, we can see I'm speaking at dev to next, but not until October 1st. That's where the temporal component comes in there. So that's like a simple graph example of constructing the graph. We can also go to the memory search here, and if we're searching for something related to national parks, we're going to do calculate an embedding of this query, do a vector search, and then traverse the graph. And so we get back kind of like a summary of the graph plus vector search here. And so we can see here like the top matching entities, Yellowstone National Park, and then we have others that have like very low similarity scores. So we may not want to consider those. And then we have a summary of this and also like a description of each one of our entities. So this is a look at this through the MCP inspector. But what MCP allows us to do is connect um, to really any AI application that is capable of consuming MCPs. MCP clients can be embedded in lots of different AI applications. This is Claude Desktop. Claude Desktop has a project feature that I really like that allows you to save specific instructions for any chat that you have in that project. And so really all I said here is like, hey, save the chat history using the save user message tool, and then retrieve memories using the graph memory search tool. And so any chats that I have in here will use those instructions. You can think of that as like an agent prompt essentially. And the nice thing about Claude here is that Claude, I think, is a really good example of taking advantage of leveraging like all of the features of MCPs. If I wanted to include things like the resources, the prompts, or also if we look at in the inspector, this is a great way to see to like how the MCP ecosystem is evolving, which is quite neat. There are all kinds of interesting things in here, like sampling. Um, so sampling allows us to have the MCP server request sampling from the LLM, elicitations, where we can request more memory from the user. These sorts of things I think are quite interesting. Cool. Okay, so we're about out of time here. I think we've covered a lot of what I wanted to cover. I'll skip kind of going through a code walkthrough. I'll drop the GitHub link in here again, and we can kind of see how this works. I think the important like pieces here are that we're leveraging the Model Context Protocol SDK for creating MCP servers, which is really nice. There's a really good one for Python. This is the SDK for TypeScript. And then we have a library here that has kind of two implementations, one for dgraph, one for Neo4j for the database piece, where you can kind of see in here like the cipher queries that we're using. And then we also have something similar for the AI sort of wrapper pieces that work for either Anthropic, OpenAI, or Olama running locally. Cool. Let's see. So it looks like folks are familiar with building MCP servers with Python in Vercel. Cool. That's awesome. So a question about named entity recognition using LLMs versus old school things like Spacey. Yeah, this is so the question essentially is like, hey, you're using this prompt to extract entities, and then some other options for entity resolution. How does doing this compare to some of the some of the sort of language methods like that are more probabilistic, essentially, I guess is maybe the way to phrase that. And that's a good question. Like I'm not sure. I haven't like read the papers to see the comparison. I see people using both options in similar projects. I don't have a good answer to that, honestly. I think that using using LLMs is for entity extraction seems to be performing well. One thing that I notice, a lot of the concepts or sort of shorthand for referring to entities doesn't translate well. One thing that I included in this project is the where is it? The Locomo benchmark. I think I have a script. Yeah, so Locomo is this data set for AI agent memory benchmarking. And so included a script here to import that and kind of run through the benchmark a bit just to have some I don't know, some numbers on kind of how this sort of system performs to others. So that was something I noticed, is that a lot of the things that aren't quite actual concepts or maybe refer to ideas or places as almost as like pronouns essentially get treated as entities. So I think there's some tuning there that needs to happen with your prompts in the LLM. A lot of the other language tooling I think have been tuned over time and have a lot more interaction and updates there. So something to dig into for sure. Yeah. Cool. Well, let me see if we have any last few slides to talk about, and then we are about out of time here. So where are we? We're all the way back at the beginning. Let's jump to the end here real quick. Cool. So we went through all this. We saw a demo of how to use these concepts with Neo4j and Claude Desktop. I think a couple of outstanding questions, other than some of the ones that we talked about, are like how should these memory tools be exposed to agents? Like, is that really the framework's responsibility? Does the MCP approach work well? One thing that I think was interesting is, with MCP, you have a couple of options. Is like you can have the AI application, like the agent, essentially be responsible for doing the entity extraction and these sorts of things, and then it just calls a tool that says, "Hey, update the graph." There's a implementation of knowledge graph memory in the Anthropic Model Context Protocol repo that does essentially this, where you're essentially putting the onus on the AI application to do the entity resolution, do the sort of fact resolution, that sort of thing. Whereas here, all of that logic is sort of hidden behind the MCP tool that's exposed. Another sort of thing to look at is how do we apply our own business domain to the graph model that is created. What we saw here was quite generic, right? We just told the model to come up with something like, hey, come up with a simple, short works at, traveling to, that sort of relationship. But what if we have a explicit domain model already that we want to use? This, I think, is one area where the models over some of the more traditional language processes offer some advantage, because we could potentially apply through like the types we've defined, or maybe like a pydantic link or something like that. And I know Graffiti and Zep is actually working on this piece now, where you're defining a bit of the schema that you want to be applied in the graph that you build. Cool. So I think those are the issues that are, I think, a bit outstanding at this point. So areas for further research and so on. Cool. So we're a bit over time. So I think I will stop there. But thanks everyone for joining today. This will recording will go out on YouTube. You can grab the slides there, graphstuff.com/agent-memory. I'll put the link into that in the chat. So from the slides, you can grab any of the links to the code that we talked about, which I'll also drop a link to that in the chat. I see someone asking about link to the GitHub repo. Cool, there it is. Great. Well, thank you, everyone, for joining today. Thanks for Amy and the GraphGeeks community for hosting and organizing. Great to see everyone today. Feel free to ping me in the Discord. That's I think kind of the best way to find me. Oh, I see a question there about how do you apply to speak for GraphGeeks. I think the best way to do that, if you're interested, is to join the GraphGeeks Discord if you're not in there already, and just kind of find one of the channels I think that are interesting based on your areas of interest within the graph ecosystem, just to kind of engage with the community there. But ping Amy on Discord if you're interested in doing a presentation. I think she can definitely help help you get that scheduled. Cool. Well, thanks a lot. Thanks again, everyone. Again, my name is Will, and you can find me in the GraphGeeks Discord if you want to dive into this topic a bit more. But yeah, thanks for joining, and we will see you next time. Cheers, everyone. Bye-bye.